Hello everyone, I will continue our discussion on linear quadratic regulator theory. Previous lecture we have derived, we have discussed the concept of LQR design as well as derived the necessary conditions. We followed up with Riccati equation derivation as well as some examples actually. Okay. In that example, inverted pendulum example especially, we discussed about the stability behavior and things like that. So, we will continue further with that generic descriptions and all that. There are many things that we can discuss under the LQR design, and we will cover some of the important things that comes up associated with design actually. Okay. So, outline of this particular lecture will be like this. So, we will first study the stability and robustness properties of LQR, and we can also see there is a optimum value of the cost function directly we can see in terms of LQR solution, Riccati equation solution. And we can also see some extensions of LQR design. Okay, the cross product term in the cost function, the rate of state minimization, what happens, all sort of things. Those are some of these things we can discuss, and we can also talk about LQR for command tracking as well as LQR for inhomogeneous systems. Some of those things will be a practical usage for many different problems actually. So, let us start discussing one by one and see how these things are in place. So, first is stability and robustness properties, and first we will deal with the stability part of it, and here I assume that you are somewhat roughly accustomed with this Lyapunov design, which we are going to study in our lecture series little while later. But all that it matters is when you have a homogeneous system, okay, and the closed loop system turns out to be a homogeneous system. Okay, this is x dot is a x plus b, but b equal to minus kx. So, closed loop system is x dot equal to some matrix into x, which is nothing but a homogeneous system. And if you have a homogeneous system like that, the way to use Lyapunov theory is you select a Lyapunov function v of x, which needs to be a positive definite function, and as soon as we as long as we select a positive definite p matrix, this particular function is certainly a positive definite function. Okay. So, we given a homogeneous system, we select a positive definite function, and somehow we make sure that the time derivative of this function is actually a negative definite function. Okay, then the system is asymptotically stable actually, that is what it tells. And along with that, if the function is actually radially unbounded, and here everything will be satisfied that those conditions, and certainly the function this result tends to be global actually. Okay, that means it can be shown that the system is globally asymptotically stable. That is what we want to do here. Okay. So, we have this closed loop system dynamics, and you have the Lyapunov function candidate like this, which is certainly radially unbounded. We will see some of these concepts later in later classes actually. Okay. Then we can think of doing this time derivative now. The v dot is nothing but starting from here, it is this one, and remember all these things we are talking about constant p matrix solution, the infinite time problem actually. So, v dot turns out to be like this, x dot transpose times p x plus x transpose times p x dot, and x dot is nothing but that a minus b k into x. Okay. So, a minus b k into x here, and that transpose is there times p x plus x transpose p times x dot. So, x dot is that actually. Okay. So, we put them together and then tell okay, this transpose can be expanded in a reverse sense. So, x transpose turns out to be like that, and a minus b k transpose turns out to be that way, and k remember is nothing but r inverse b transpose p. So, that is the k. So, wherever k appears we will take that way. Okay, we will substitute that, open this bracket, now it will become a transpose here, and the transpose will multiplication transpose will happen in a reverse sense. So, that is how, but remember p is a symmetric matrix. Okay, so, p transpose is equal to p. So, all sort of things we take advantage while simplifying this, and then what you do is you do a plus and minus q, add and subtract q matrix actually. The whole purpose of doing that is we have some bunch of terms outside, but one part of the exercise turns out to be nothing but algebraic Riccati equation in the left hand side. So, this is certainly equal to 0 on the optimal path. So, this is gone. Okay, as long as we apply this controller, optimal controller minus kx, where k is nothing but r inverse b transpose p, and then this equation is satisfied. So, that means this entire equation what we see here is going to 0 actually. Okay. So, once that is entire thing is gone, we are left out with only these last two terms. and that is how what our V dot turns out to be like that. So, if I take the negative sign out also, okay. So, let me take the negative sign out. So, this is nothing but minus x transpose, okay, x transpose q plus p b r inverse b transpose p into x. Okay. So, all that we need to show is this particular matrix turns out to be positive definite. Once you are there, the negative of that is certainly going to be negative definite function, then we are done actually. Okay. Now, the question is this matrix what you see in bracket is it positive definite? Now, one part is here that Q what you see is Q matrix is positive semi definite by requirement actually. Okay. So, that part is positive semi definite anyway. So, all that we need to show is this part remains positive definite actually. Okay. Now, because R is positive definite, R inverse is also positive definite. Okay. Why? Because eigenvalues of any matrix or nothing inverse of a matrix is 1 by eigenvalues of the matrix actually. So, if R is positive definite, its eigenvalues are positive and hence 1 by those eigenvalues are also positive and hence R inverse is positive definite matrix. P matrix by selection is a positive definite matrix anyway. So, we are multiplying both sides by positive definite matrix, and B times B transpose is like a quadratic term actually. Okay. So, this entire process makes it this one positive definite matrix. That is what is written here. R is positive definite, so R inverse is positive definite, P is also positive definite, and B and B transpose acts like a quadratic term out here, and hence all the things that happens to be positive definite. Also that Q is positive semi definite, and hence addition of the two is certainly a positive definite matrix. Once this is a positive definite matrix, B dot is that, so it is certainly going to be a negative definite matrix, and hence this B dot is negative and the closed loop system is always asymptotically stable, no matter whatever values of P and Q and R you select. Okay. This as long as you satisfy that Q is a positive semi definite matrix and R is a positive definite matrix, then V dot is certainly going to be negative definite, and hence the closed loop system is always asymptotically stable. And as I told before, because this function is also radially unbounded, this result is actually global. So, the result does not, in other words, starting from any initial condition, we are certainly guaranteed to go towards 0 actually. Okay. So, that is the powerful result that you can rely on in LQR theory. Now, what about the minimum value of the cost function? Can we compute a priori as a cross checking of our result verification on is a kind of, it may serve as a verification tool. So, let us analyze this cost function, and so J is nothing but T0 to infinity, this quadratic term, and then U is nothing but minus R inverse B transpose P. So, we can substitute U that way and then the transpose there, and then expand this transpose. Okay. Then R inverse transpose, right, will come here, and then R times R inverse is identity and all that actually. Okay. So, R is certainly a positive definite square matrix roughly. So, I mean is positive definite square matrix. So, R inverse is also a square matrix, it is a symmetric matrix also. So, R inverse transpose and all will be nothing but R inverse itself actually. Okay. So, you do this algebra and then tell, okay, this particular thing x transpose is all multiplying left and x multiplies right. So, this turns out to be like this. Okay. So, this particular thing remember this what you see inside the bracket is nothing but negative of V dot, that is what we just saw actually. Okay. This is negative of V dot. So, I can substitute this term as negative of V dot. Okay. And then I can see that it is nothing but derivative and integral of a derivative term. So, I can just simply take V, okay, and T0 to infinity now, you can evaluate that, and it turns out to be like that actually. So, if I evaluate this term, this turns out to be negative sign is there, remember that. So, infinity minus T0 or negative sign included, it is initial condition minus final condition actually. Now, final condition sense except x infinity is 0 anyway, because that is what we are guaranteed to get using this asymptotic stability condition and all that. Okay. So, once that is there, then the cost function of the LQR turns out to be this way. So, it is half of x0 transpose P times x0 only. So, starting from any initial condition, we can actually compute the final value of the cost function, and certainly this can give us some sort of a verification tool whether our control design is proper or not in the simulation studies actually. Okay. So, that is the value of a cost function actually. Now, there are robustness concepts as well, which tells us that under the ideal condition of exact state feedback and all, your system will have a very good robustness margin, with where gain margin turns out to be infinity and phase margin turns out to be 60 degrees actually. More on that is available in this book. We will not digress so much into that, but you can see these things that are available. This guarantee is also there in addition to global asymptotic stability condition basically. So, that is how this design is a powerful design actually. Okay. Now, extensions of LQ, but okay, before I proceed further, also remember the moment there is this states are not fed back in exact sense, that means you consider this so called LQG design and all that, where the state needs to be estimated through an observer or filter, then these properties are lost actually. Okay, that is a major drawback, major hurdle actually, and then that is why people talk about LQG/LTR design. That means that LQG design turns out to be LQR design with Kalman filter based state estimation, and then LTR is something called loop transfer recovery and all that actually. Okay, so, those are concepts that are available from the LQRs, I mean the linear quadratic design details and all that. Those of you are interested can see some appropriate book actually. Okay. One of that book is certainly this book actually, you can also see details of that here. Alright, so let us study about some extensions of LQR design. We will study about bunch of about 3-4 extensions. So, let us see how that proceeds. First is the cross product term in the performance index. Before we did not talk about this particular term, where x and u were not together, either x transpose qx were there or u transpose ru were there. Now, some applications you may come across where this cross product term also becomes a necessity in the performance index. Then how do you do that? Now, whole idea here is not to go back to these necessary conditions of optimality and then try to rederive the similar form of Riccati equation and all that. We are not interested in doing that actually. What you are interested is, can we reformulate the problem in a slightly different way, so that you can interpret the same problem as an LQR problem for a different system, and then utilizing that solution, can you come back to this original solution actually, I mean original problem solution. That is the whole approach here. Okay. So, to proceed in that with that philosophy, what we do here is we take this quadratic expression, okay, and we can see that this particular quadratic expression, okay, this one we want to visualize as some form of quadratic expression actually. Okay. Now, it turns out that if you consider this expression, this is a little complicated longhand expression. Nevertheless, if you consider this, then try to simplify this, transpose, multiply and cancel out corresponding terms, things like that, then this term is same as this term actually, what you see here. So, instead of having this term out there, I can visualize the same cost function in terms of that. Okay. Now, what is beauty of that? Now, this is my state anyway, so I leave it aside. I can visualize this term as some sort of a different Q matrix, let us call that as Q1 or something, and I can visualize this as a different control. Okay. So, with respect to that particular Q and that particular control vector, I now have some sort of a quadratic form, and that is what I am doing here. So, I substitute that back here, I consider that as Q1 and I consider that as U1, and hence it is something like Q1 this x transpose Q1 x plus U1 transpose RU actually, RU1. Okay. So, that is how I will visualize. So, this is certainly a quadratic cost function. Okay. And then the problem is not over, because we had the original state equation this way. It was not in terms of U1, it was in terms of U. However, once U1 is that, you can solve for U from there and substitute substitute U as this expression U1 minus that actually. Okay. So, now you can combine x side of the story and then tell, okay, this particular thing that pops up is nothing but A1 and that is my U1. So, in other words, you have a problem for x dot equal to A1 x plus B U1 and J is nothing but that. So, now this linear equation in terms of x and U1 and A1 B matrix, okay, this linear equation with this quadratic cost function, you can have a regular LQR formulation actually. So, we can get a solution from that particular problem like this, U1 equal to minus kx, but U1 is not our ultimate objective, U is our ultimate objective, but U is like this, u1 minus that. So, once u1 is there minus kx, I can substitute that and get my solution ready. So, this is the real gain actually, k plus r inverse w transpose is our real gain matrix that you are talking, which comes through a virtual gain matrix k for a related problem in the setting of in the LQR framework actually. Okay. So, we really do not have to go back to this entire idea of necessary conditions, start deriving the Riccati equation again and things like that. That is not necessary here. Okay. So, that is how we handle cross product terms in the performance index. Now, let us see whether second condition, okay, weightage on rate of state. Okay, sometimes it is also essential to minimize the rate of state in addition to state itself. One of that, as I told in the inverted pendulum case, you have to minimize theta and theta dot as well. Sometimes it is also advisable to minimize theta double dot as well actually. So, for better and better guarantee of inverted pendulum stability actually in a way. So, anyway, so some problems it is not enough to minimize only state, but their derivatives as well. Okay. And in those situations, I mean that is actually like suppression of noise and other things are there. I mean that will lead to that part actually. Okay. So, once you have a term something like this, it is equivalent of telling that okay, x dot is x plus vu. So, I put x dot equal to like that way, okay, and x dot transpose is that transpose. So, expand this term, try to simplify that, to combine the terms and things like that, you will essentially end up with this simplification actually out here, which I can interpret this as a cost function that way, which has a quadratic term in x, a pure quadratic term in u as well, but there is a cross product case also. So, we now with this particular formulation leads to a case of cross product terms being there. Okay. Now, we know how to handle this cross product term already, okay, and hence we know how to solve this actually. Okay. So, that is how we handle this rate of state. Now, there is another thing which another extension which you tell okay, what about rate of control? If you have rate of control, that is also another robustness formulation sort of thing, where we need to minimize the rate of change of control variable as well actually. So, if you have that, the solution is not very straightforward rather, but still it is doable, possible. Okay. So, in that sense what I do now, let us say I will visualize this u dot as a virtual control variable v and consider u as a state variable actually. Okay. So, I have a augmented state vector which is my original state and control vector, that is my augmented state vector, and v is my virtual control is nothing but u dot. Once this definition is in place, then the cost function j what we already had here can be visualized that way. These two terms I will combine through this matrix, okay, this term, and u dot r hat times u is nothing but v transpose r hat times v basically. So, we have a quadratic looking formulation like this, okay, in terms of an augmented state vector x and u basically. Now, we need to do further things because the original problem is not in terms of x dot, this bold x dot, but normal x dot actually. So, what about those things? So, we will go back to that. Okay, this is our system dynamics, x dot is x plus bu. Now, we have an augmented state vector where u dot is v. So, if I put that together, that is my big the bold x dot, it turns out to be that way. So, we have got an a hat and v hat matrix popping up from here. Okay. You can observe two things. One thing is the dimension of the problem has increased from n to n plus m. The original state vector was n, original control vector was m. So, now the dimension of the state big X actually or bold X turns out to be n plus m. So, the Riccati equation dimension, the Riccati matrix dimension is no more n by n, but it is n plus m by n plus m actually. So, that is the dimensional increase actually happens. Second thing, it is more important actually that if A B pair is controllable, it turns out that A hat and B hat pair is also controllable, and I encourage all of you to kind of justify that in your own math actually, algebra. You verify that you formulate a controllability matrix for the A hat and B hat pair, and you also know that A B pair is controllable, okay, that is there is a different controllability matrix for that, and that is full rank. So, you can show that the new controllability matrix is also full rank actually. Okay. So, it turns out that if A B is controllable, the new system dynamics that you see visualized here is also controllable actually. Now, the solution turns out to be like this. Ultimately, you get a solution of in terms of V as a function of bold x actually. Okay. So, that means minus r hat inverse thus B hat transpose B hat times x actually. Okay. where p hat is a solution of that. Okay. Now, this so what I am telling here, once you get v is nothing but u dot is that. So, expand all that, and this one turns out to be like this. So, this is certainly a differential equation, okay, in terms of control variable, which makes the controller dynamic actually, which we do not want to operate that way. Most of the time dynamic controllers have their own problems actually. So, we want the control as a static function of x or its integral value, that where I can make use of the past history of x actually. That is what we intend to do here, but while intending to do that, this u needs to be kind of eliminated from the right hand side. Now, how do we do that? We take advantage of this one, okay, the x dot is x plus b u anyway we know. So, u is turns out to be this solution, where b plus is nothing but the pseudo inverse of b. Remember, this b is not a square matrix in general. So, we cannot talk about b inverse here, and that is where this approximate solution and things like that comes in here actually. Okay. So, okay, anyway, we will not talk too much on that, but then what happens here is u I can solve it from here using this pseudo inverse solution, right, and because this is over constrained problem, the pseudo inverse solution is typically not a good solution. That is my own personal comment out here actually. So, do not jump into this idea unless this is badly required. Anyway, once I solve this u in that way, then I can put it back that u dot turns out to be that one, and hence I can visualize it partly as a function of x and partly as a function of x dot basically. Okay. All right. Anyway, this bracket will terminate somewhere here. Okay. So, that is not there. This whatever you see as coefficients are actually the definitions of k1 and k2. Okay. Alright, so that is obvious from the expression as well. So, this is u dot is nothing but minus k1 times x dot minus k2 times x. So, now I can integrate both sides and visualize that okay, u is a proportional gain. Okay, u is minus k1 times x. Okay, that means it will throw me a proportional gain, and okay, as a proportional term actually you can say that way, k1 times x together sort of thing. There is a proportional feedback and there is an integral feedback, and there is an initial condition for u that will also be required actually. Now, how do you get this u0? And my suggestion is you consider a performance index, a parallel problem without this term. So, that is a regular cost function anyway, and there you get a solution for u that you consider as u0 actually. Okay. So, that is that is how I will recommend actually. Okay. So, that is how you get a control, where the control is consisting of three parts. One is the proportional part, and there is the integral part, and there is the initial condition part actually. Okay. Anyway, so that is it leads to this PI sort of controller, okay, and this u0 can be obtained from a regular LQR formulation actually. So, that is our third thing. Now, what about fourth extension? Okay. Now, here is a problem which talks about okay, the asymptotic stability guarantee is all good, but it tells me that the eigenvalues are only located at left half side actually. Now, if that is the case, then some of the eigenvalues can in fact be located little too close to this imaginary axis actually. If it is too close to that, then because of this parameter inaccuracy in other problems, other practical problem, there is a chance that some of the poles that are situated close to the imaginary axis can jump to the right hand side, and then my system will go unstable actually. So, to avoid that situation, can I guarantee that all the eigenvalues are situated left of an artificial line a b, which is situated by a distance alpha from the imaginary axis. If a b line is situated by a distance alpha from the imaginary axis, so that I have at least this much of margin, and if at all there is an inaccuracy of parameters and all, the poles located out here can only go to that side, which is still in the left hand side of the j omega axis. So, this is actually some sort of a robustness consideration actually. Again, can we do that? It turns out to be yes. The answer is yes, we can do that by selecting a cost function this way. Okay. Let us say the performance index, if you select that way with an augmentation of e to the power 2 alpha t there, then it turns out that we can do it. How is it possible? Let us analyze that. So, this 2 alpha t is nothing but e to the power alpha t into e to the power alpha t. So, I put e to the power alpha t one term here, one more term here. So, that term I visualize that way, and similar thing I do it there and define this x tilde u tilde vectors that way now. So, I can talk about this because the cost function is nothing but that actually. Okay. So, it is a quadratic term in terms of x tilde and u tilde variable. Okay. So, now can I proceed further, because this cost is this original equation also I need to transform. There I need to analyze this x tilde dot actually. So, if I go back to the definition x tilde and to make x tilde dot out there, that is the form, and x dot is x plus bu. Okay. So, that is the form, and wherever I can, e of alpha t is a scalar quantity. So, I can take it anywhere I want. So, I can combine with x and u, and then I can combine these terms associated with x tilde. This is x tilde, this is u tilde, this is also x tilde. So, I combine this first and last term. So, that is a plus alpha e times x tilde plus b u tilde actually. So, the control solution from ultimately what you are getting from this, this solution control, what you are this is the linear system equation, and that is the cost function. With respect to that LQR formulation, I can get a solution this way, u tilde is minus k times x tilde. So, u tilde is e to the power alpha t times u by definition, x tilde is also that. So, e to the power alpha t e to the power alpha t gets cancelled out, and all that you are left out is okay, these terms get cancelled out, you are left out with u equal to minus k x. So, the same gain that you are computing through a alternate formulation is nothing but the feedback gain that you would want to operate your actual controller actually. Now, how does that eigenvalues are shifting? I mean, getting shifted from the imaginary axis to this boundary sort of thing, I mean left of a b. Let us see how that happen. You can see that the modified system is like this, u tilde is minus k x. So, x tilde dot is something like this. Okay. The actual system is like that. Okay. So, what do you see? I mean, this entire formulation, the way this gain matrix and other things are I mean, the entire formulation what we are discussing here guarantees stability for this system dynamics, asymptotic stability. That means, for this particular system, the closed loop eigenvalues are situated left to the imaginary axis. Okay. But remember, this is alpha e term, which can only modify the diagonal elements of the characteristic equation. If I take a characteristic equation of for this, I am only modifying the diagonal elements actually, I mean diagonal elements, and hence if I interpret the eigenvalues of this, okay, I can take out those thing and then tell okay, this alpha I, all these eigenvalues, the real part of those values will be getting shifted by negative alpha actually. Okay, I have to subtract minus alpha from the solution of that really. That is how we get this desirable condition that all the eigenvalues, where whatever all the eigenvalues are getting shifted by alpha 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 to the left actually, that is what happens. So, if something is shifted, something lies here, that also gets shifted by alpha distance basically. That is how we guarantee this prescribed degree of stability actually. Okay. So, that is how it is happening there. Now, let us study one more thing. So, that is LQR design for command tracking. Okay. How do we do that? Okay. Now, here is a problem which the problem is something like that. We need to design u for command tracking issue now. In other words, earlier we are mainly worried about x should go to 0 only, that is the regulator problem, and that is where the LQR system has been designed, I mean for that particular problem only actually. Now, if you want to extend that to the tracking problem, how does it happen? Here we instead of considering a very generic problem and things like that, what you are telling here is, let us say the x vector is divided into two parts, okay, where xt and xn, where xt is the tracked states, okay, that is what we want to track actually, okay, and xn we are typically not bothered about that so much actually, it can go somewhere, we are not so much concerned about that. Okay. For example, again if you go back to that inverted pendulum example last lecture, what we discussed is theta needs to go to 0. So, let us say theta dot we did not put any condition on that actually. Similar, something similar you can visualize, theta should go to some commanded function RC of t, where xn I mean theta dot and all we are not bothered so much on that actually. Okay. So, that is left out free, that kind of problem we are talking here actually. Okay. So, what you do here is, you are not going to revisit the entire problem, what you really need to do is I mean the whole idea here is, you typically select a Q matrix this way, QTT and QNN is nothing there here. So, QNN is left free, and off diagonal you do not normally put anything, that is anyway 0 0. Okay. But once you get a solution for this LQR problem, you operate the controller that way. Okay. So, u equal to minus kx, x is the xt and xn, instead of making it simply xt and xn, the first part of the thing you change it to xt minus rc and then make xn actually. So, that is if you operate it that way, then xt will go to rc actually, and pictorially visualize something like this. So, the LQ regulation problem operates this way, that means u is going there to be and all this thing happens nicely. But here in tracking problem what you are telling here is okay, there is a summation block out here where xt minus rc is the something that will be fed to the gain matrix actually. Okay. So, if you do that, what happens is xt minus rc will go to 0 and hence xt will go to rc basically, that is the whole idea there, under the assumption that rc dot is probably 0. I mean that is the assumption, but that assumption is like quasi steady assumption. At every time of every time grid you assume for every delta t duration we assume that rc remains 0. I mean rc dot remains 0, that means rc is a fixed quantity there. In other words, if rc changes to some value, like let us say rc changes like that, then you assume that this remains kind of this changes that way basically. Okay. And that is what a normal assumption for okay, this is rc and this is t actually there. Okay. All right. So, this is a normal assumption in tracking problems, what you call as quasi steady assumption. It is not really steady, but for every delta t it is assumed to be steady actually. So, under that condition it can be shown that it is xt will go to rc real, because xt minus rc will happen to be 0 basically, that will go to 0 basically. All right. So, now there is a problem of this particular thing. When you talk about tracking thing, typically people are interested in having a integral feedback in the loop, and let us see how to do that. So, what you do here is we want to have an integral feedback in the loop. So, we augment the state vector in terms of an integral state actually, xi dot is xt. Okay. So, xi dot is xt means this will become like a additional integral state basically. Okay. And then the feedback solution will operate that way. So, you have partly the proportional term, the difference error, and the non track states, and there is a integral of the tracking error that will come as a feedback to that actually. Okay. And correspondingly you have to select a gain matrix for the integral part as well. Okay. You can leave the non track states to 0, but this will become a like it is not really a 3 by 3, but it is a blocked partition sort of thing, but the last block what you are talking should also contain some sort of a weighting matrix out there actually. That is what we are telling by select the appropriate Q matrix actually. Okay. So, it penalize both xt and xi states. Now, the control solution should operate it that way. Okay. All right. So, LQR next we see LQR design for inhomogeneous system. Okay. So, that is let us say what we are talking here is okay, inhomogeneous system, that is I have taken this from here. So, obviously, it is a I mean this idea is not very new, all these ideas are actually not very new, it is long time back people have studied this and all that, but still they are useful in variety of conditions actually. Now, okay, this is also aerospace application. Those of you are interested in looking at how this particular formulation is useful for missile guidance, they can see this paper actually, and they can see this utility of this for missile guidance problems. Now, the core part of it is you have actually an inhomogeneous system. Okay. What does it mean is I mean what does it mean? This means that instead of x plus bu only, you have a plus c term also. So, that means x dot equal to x plus bu plus c is there basically. Okay. Now, if you have this kind of a thing, how do you handle this? Okay. That means you can visualize this as a constant input. For example, let us say there is a constant wind flowing while your aircraft is flying. So, then how do you handle that? Is actually a bias term which is trying to push the aircraft all the time actually. Now, let us see how do you handle that. Okay. So, there is no direct extension per se that we will discuss here, we have to go back to the Hamiltonian and necessary conditions, things like that actually. Okay. Anyway, so let us study this cost function is same, I mean what we started with, and similar conditions hold good actually. So, now we go back and okay, this is our kind of performance index, but the state equation becomes something slightly different. It is plus C terms out there. Okay. Hamiltonian will also get different, because of that there will be a plus C term there, and the corresponding equations will take its own form actually. So, you can see that any derivative of constant C is actually 0, and hence this lambda dot, which is partial derivative with respect to x, and then this is partial derivative with respect to u, the optimal control equation will not change, because that term will not contribute to any additional term anyway. Okay. So, co-state equation will remain like that, and optimal control equation will remain like that. Okay. Now, how do you handle this kind of situation? The state equation, however, remains like this. The whole idea here is, because there is a constant bias here, let us try to kind of visualize a constant biased control, which is which essentially needs to nullify that bias actually. So, if you see that, then lambda, the ultimate control that I am looking for should have a bias term, and hence lambda should also have a bias term actually. Okay. So, let us with that philosophy, let us start with this thing and tell, okay, lambda is not only a linear function now, but it is something like a straight line equation sense is sort of idea, where I have this k of t in addition to this term actually now. Okay. Let me see that whether I can handle this problem through this this type of a lambda solution or no actually. Okay. Now, if I have this lambda form known to me, then lambda dot turns out to be like that. Okay. This is p dot times x plus p times x dot plus k dot. This is very obvious from there. K dot part I will not change, it will remain, I will keep it, but x dot and all I will start changing. Remember, state and co-state and optimal control equation will not change too much actually, only state equation will change. So, that is where x dot will become like that, and then because u is R inverse V transpose lambda, I will put it that way with a negative sign, and then I will try to P c will come out from here, and lambda is again P x plus k this time, is not is now no more P times x only. Wherever lambda is there, it is P x plus k, and wherever lambda dot is there, okay, that is q minus q x plus a transpose lambda basically. Okay, minus q x plus a transpose lambda, where lambda is P x plus k this time, one more time. Okay. So, P x plus k comes here, P x k comes here, and x dot equal to x plus b u plus c comes here actually. Okay. So, because of all these things together, now I try to simplify it, attempt to simplify it, and then take all the terms to the left hand side, and then what happens here is, okay, this similar form of Riccati equation pops up with a which is multiplied with x plus, okay, there is a plus term missing out here probably, plus, okay, this term has to be 0 actually. Okay. Okay. Now, what happens if I really want to make this thing equal to 0, then the way to do that is, let us say the coefficients will go to 0, and hence I will get two equations, not one, but two equations I will get. One is the Riccati equation, standard Riccati equation. Another equation is something like auxiliary equation actually. So, that means k dot equal to A transpose minus P V R inverse k, whatever it turns out from here, that is an auxiliary differential equation. So, if I really need to know P of t and k of t, differential equations are ready, but I need to talk about boundary condition as well, and the same boundary condition holds good here basically, because the outside term was not changed, outside term remains same actually. Okay. That is why phi remains same and lambda f remains same. So, let me satisfy this term, this equation. If I put the boundary condition out here and try to equate the coefficients, what it turns out is P of T f is equal to S f and K of T f is 0. So, if with K of T f 0 and this differential equation, I can propagate back, integrate this auxiliary equation backward from T f to T 0, and with this boundary condition and this differential equation, I can integrate the equation backward actually again. Okay. So, I will have the solutions for both P and K ready. Okay, that can, with this integration process can again be done backward, and make sure that you store these things, these solutions and all on board. So, you have the solution ready offline, and then you can use it online actually. Okay. So, you are using these two differential equations and these two boundary conditions, you can actually solve these equations, and then you are ready to apply the controller, because lambda of t after that is like this, and u of u is equal to minus r inverse b transpose lambda, where lambda is like that, which is known to us. That is what I am doing here. control solution turns out to be like that, and the control solution, if you see carefully, what it turns out is this U has a proportional term like an LQR controller before, but it has a bias term also basically. Okay. So, what it turns out is that the residual controller even after x goes to 0, this is the term. Okay. So, there is a residual controller which will naturally come after x goes to 0, and this residual controller part actually tries to offset the continuous disturbance C, that is the meaning actually. Okay. So, that is the way to handle this. So, what we have seen in this lecture is extensions of LQR control design in various forms, as well as how do you extend it for, let us say, command tracking and inhomogeneous problems. We also saw stability and robustness behaviors. I suggest that you can select some proper book on LQ design and study more actually. So, with that I will stop this lecture then. Thank you.